the second and last part of this lecture, we'll look at a couple more examples of precipitation reactions and their applications. The first example would come under the heading of something called selective precipitation of ions. So let's set up our example. Let's suppose you have 250 milliliters of a solution that is both 0.0100 molar in silver nitrate and 0.0100 molar in copper nitrate. So this solution has silver ions, it has copper ions, and it has plenty of nitrate ions. And the concentrations of silver nitrate and copper nitrate are both 0.01 molar. And again, you have 250 milliliters of this solution. Now let's suppose you start dissolving measured amounts of sodium chromate in the solution. Now sodium chromate would come in the solid form, and this may seem like a rather random thing to do, but what we're hoping to do is to first cause precipitation of silver chromate or copper chromate, but not both simultaneously. So that's why this example comes under the heading of selective precipitation of ions. Again, we have a solution with silver ions and copper ions. The nitrate ions will be spectators here. You start dissolving sodium chromate, which will give you sodium ions and chromate ions. And what you're hoping is that the chromate ions will go after either the silver ions or the copper ions at first, but not both. So we're wondering whether we're going to get precipitation of silver with chromate, silver chromate, or copper with chromate, copper chromate. Well, the idea here would be to attempt to use a precipitation reaction to separate silver ions and copper ions. Now, chromate salts, when they form, are typically yellow. This is a common color for a chromate salt, so you might see, when you do this experiment, a precipitation that looks something like that. So we have some questions here. Of course, what would be the first compound to precipitate? Silver chromate or copper chromate? What concentration of chromate ions would be necessary to start precipitation of the first precipitate? What concentration of chromate ions would be necessary to start precipitation of the second precipitate? How many grams of sodium chromate will have been added to the solution at the point where the second precipitate just begins to form? What concentration of the first cation to precipitate will remain in solution at the point where the second cation just starts to precipitate? This gets to the issue of whether or not we can separate these two ions with a precipitation reaction. And we have a couple of KSP values here that we'll deal with. And again, remember the sodium ions that are added with the added sodium chromate and the nitrate ions that were there originally in the 250 milliliter solution would simply be spectators in these reactions. Well, an understandable reaction to all these questions would be, I have no idea where to start. We can actually address the first three parts, A, B, and C, with some quick calculations. So let's attempt to do that. Let's calculate which compound would require the lowest concentration of chromate ions to begin precipitation. So what I mean by that is we want to precipitate either silver chromate or copper chromate, and what we'd like to know is which one of these would require the lowest concentration of chromate ions to begin precipitation. That would be the one that precipitates first. So let's calculate that. For silver chromate, we can calculate that by writing out the KSP expression for silver chromate, which would be here. Remember, the silver ion concentration would be squared because there's 2 silver ions in this formula. And what we know is, we know the concentration of the silver ions. It's 0.0100 molar. So we'll put that in here and square it. What we don't know is the concentration of chromate ions needed to make this expression equal to the KSP value of 1.2 times 10 to the minus 2, because that would be the concentration that would make this expression equal to the KSP, which would be the point at which the chromium or the chromate added would just start to precipitate silver chromate. So let's get on with this here and calculate the concentration of chromate needed, and the concentration is 1.2 times 10 to the minus 8 molar. So this would be the concentration of chromate required to just begin precipitation of silver chromate. How about for copper chromate? Well, let's do the same exercise. Write out the solubility product for copper chromate, fill in the concentration of copper ion, which we said was 0.01 in the solution to begin with, and calculate the chromate ion concentration needed to get this whole solubility product equal to the KSP, and it turns out to be 3.6 times 10 to the minus 4 molar. That would be the chromate ion concentration required to just begin precipitating copper chromate. So we have the answers now to parts A, B, and C. The first compound to precipitate upon addition of solid sodium chromate, which is how we're adding the chromate, would be silver chromate, since it would require a lower concentration of chromate, 1.2 times 10 to the minus 8 molar, to begin precipitating than would copper chromate. So we've actually answered the first 3 parts here. What would be the first thing that precipitates? Silver chromate. How much would be required? What concentration of chromate ions would be required to start precipitation of this first precipitate? 1.2 times 10 to the minus 8 molar. What concentration of chromate ions would be necessary to start precipitation of the second precipitate? You'd have to get the concentration up to 3.6 times 10 to the minus 4 molar to get copper chromate to precipitate. Now we still have parts D and E to deal with. Part D is how many grams of sodium chromate will we need to add to the solution to get to the point where the second precipitate just begins to form. That would be to get the concentration of chromate to here. But let's go to the next slide. Well, previously, of course, we found that the second precipitate to form would be copper chromate, and that the chromate concentration required to begin precipitation was calculated to be 3.6 times 10 to the minus 4 molar. Now, assuming no volume change when we add the solid sodium chromate to the solution, which is a good assumption, we can calculate the number of moles of sodium chromate and ultimately its mass required to get the chromate ion concentration to 3.6 times 10 to the minus 4. The number of moles of sodium chromate we would need would be the volume of this whole solution times the concentration of chromate needed times recollection or realization that 1 mole of sodium chromate delivers 1 mole of chromate ion, and we'd find out we'd need 9 times 10 to the minus 4 moles of sodium chromate. We could then just calculate the mass of sodium chromate using its molar mass and the number of moles required, and it turns out we'd only need 0.0146 grams of sodium chromate to deliver enough moles of chromate so that its concentration in that 250 milliliter solution is 3.6 times 10 to the minus 4, which will just start precipitation of copper chromate. this amount would actually be 14.6 milligrams. Now, you'd need a pretty good analytical balance to weigh out this small amount of solid precisely. Now, the final question said, what concentration of the first cation to precipitate, which is silver, will remain in solution at the point where the second cation to precipitate, which is copper, just starts to precipitate? Well, remember, the first cation to precipitate was silver ion in the form of silver chromate. So the question is asking, what concentration of silver ion will remain in solution? You've already precipitated a lot out as silver chromate, but when copper chromate begins to precipitate, maybe not all of the silver ion has come out. So it says, what concentration of silver ion will remain in solution just at the point where precipitation of copper chromate begins, where enough sodium chromate has been added to make that chromate ion concentration 3.6 times 10 to the minus 4 molar. Well, we simply need to calculate the silver ion concentration allowed in solution when the chromate ion concentration equals 3.6 times 10 to the minus 4. We can do that by using the KSP expression for silver chromate, and we say, look, we want this chromate ion concentration to be 3.6 times 10 to the minus 4. What concentration of silver ion will be tolerated to make this solubility product exactly equal to the KSP? Well, we can solve for silver ion concentration. We need to remember to do the math properly, and we find out that the silver ion concentration still in solution at the point where the second precipitate copper chromate starts to come out of solution would be 5.8 times 10 to the minus 5. Now, this is a really low concentration, so what we've learned is that very little silver ion remains in solution, 0.000058 molar, at the point where copper chromate begins to precipitate. We have reduced the silver ion concentration in solution to less than 1% of its original value of 0.0100 molar. So what we say is we have effectively separated silver from the copper, because just at the point where the copper starts to precipitate, almost all of the silver, more than 99%, has been precipitated out as silver chromate. Let's look at one more example of the application of a selective precipitation of ions. The Environmental Protection Agency, of course known as the EPA, has set what's called the action level for the concentration of lead in drinking water as 15 parts per billion. Now, a concentration of 15 parts per billion would be equivalent to 15 micrograms of lead per liter of water. Not very high. Suppose you were given a 1 liter sample of water known to contain too much lead ion, 58 parts per billion, or in other words, 58 micrograms per liter, and you were given the assignment of bringing the lead 2+ concentration in that 1 liter sample down to 12 parts per billion, which would be below the action level, using a precipitation reaction. In other words, you're looking for an anion that will interact with lead 2+ and form a precipitate and drag that lead ion out of solution, lowering its concentration to 12 parts per billion. And you're given a choice of 2 different solutions to try to use for the precipitation reaction. One is a 0.00500 molar solution of sodium sulfate. The other would be the same concentration of ionic salt, only this salt would be sodium carbonate. So you have your choice, sodium sulfate or sodium carbonate solutions, to try to drag this lead ion out of solution and get it down to a target concentration of 12 parts per billion. So the types of questions you'd want to ask is, which of the solutions would you choose to add to the lead-containing solution to most completely precipitate a lead salt, and explain why you would choose one of those. And then how many milliliters of the solution that you choose, either the sodium sulfate or the sodium carbonate solution, would be necessary to leave only 12 parts per billion concentration of lead ion in the water. Oddly enough, here we're not going for zero concentration. We have a target concentration of 12 parts per billion. Now you can make the following simplifying assumptions. One would be there are no other interfering ions in the leaded water sample, which in the real world would be a real concern. You can ignore any effects of pH on the solubility or behavior of any anion, and you can neglect volume changes caused by addition of the solution that you choose. So let's answer the first question. Which of the solutions would you choose to most completely precipitate out a lead salt? Well, you can simply write equations for both possible precipitation reactions and then ask yourself which precipitate would be the least soluble. So let's say you chose to add sodium sulfate solution to your 1 liter solution containing lead. What would the reaction look like? Well, aqueous or dissolved sodium sulfate would interact with the lead, and the lead ion, if it reacted, would go after the sulfate, form lead sulfate solid, that's what you hope, releasing 2 sodium ions in solution. And you want to recall that the KSP of lead sulfate is 6.3 times 10 to the minus 7. And when I say you want to recall that, that doesn't mean you'd memorize that. It would be something you'd look up in a table or would be given in a problem. The sodium ions here are, of course, spectator ions. Now, how about the situation if you chose to add the sodium carbonate solution to the 1 liter containing lead? Well, that would be a reaction that would look similar to the first one, only you'd end up making lead carbonate precipitate. So we want to look up the KSP of lead carbonate at 7.4 times 10 to the minus 14. So we ask which precipitate would be the least soluble. Now remember, comparing KSP values is always not the best way to compare solubilities. However, here we do have the advantage that both of these possible precipitates are 1-to-1 salts, meaning 1 cation to 1 anion. And remember, under that situation, you can directly compare the KSP values. And since the KSP value of lead carbonate is so much lower than lead sulfate, clearly lead carbonate would be the kind of precipitate you'd want to form to remove lead 2+ from the sample. So it looks like we're going to use the solution of sodium carbonate to drip in our 1 liter solution to try to drag the lead ion out as lead carbonate precipitate. So the next question was how many milliliters of the solution of your choice, our choice was the sodium carbonate solution, would be necessary to add to your 1 liter of solution to leave only a 12 parts per billion concentration of lead in the water. Well, yes, let's use the KSP expression for lead carbonate to determine the concentration of carbonate necessary to get the lead ion concentration to 12 parts per billion. Well, you know what's coming here. We haven't worked in parts per billion or micrograms per liter in problems involving equilibria. We're used to dealing with mostly molar concentrations. So let's convert 12 micrograms per liter to moles per liter. We should be able to do that by writing out that 12 micrograms of lead ion per liter times the fact that 1 times 10 to the minus 6 grams equals a microgram, times the fact that we know 1 mole of lead ion has a mass of 207.2 grams. We know that because that's the atomic weight of lead, and a lead ion is not going to weigh anything different that's significant for us from just a lead atom. So we get 5.79 times 10 to the minus 8 moles per 1 liter, which of course would be the molarity, 5.79 times 10 to the minus 8 molar. So this number here is our target lead concentration. It's equivalent to 12 micrograms per liter, or 12 parts per billion. Now let's use the KSP expression for lead carbonate to determine the carbonate ion concentration necessary to get the lead concentration to 5.7 times 10 to the minus 8. So we write out the KSP expression for lead carbonate, set it equal to its KSP value. We then solve for the carbonate ion concentration and insert the target lead ion concentration that we're looking for, and we'd find out that the carbonate ion concentration would need to be 1.28 times 10 to the minus 6 molar to get the lead concentration to be equal to 5.79 times 10 to the minus 8 molar. Okay, well, remember the carbonate's being added as a solution of 0.00500 molar sodium carbonate. So we need to calculate the volume of that solution needed to get a carbonate concentration of 1.28 times 10 to the minus 6 molar in that original 1 liter sample. Well, the number of moles of sodium carbonate required would be equal to the number of moles of carbonate required, because there's 1 carbonate in every sodium carbonate. And that would be the target concentration, 1.28 times 10 to the minus 6 moles per liter, times the 1 liter volume that we started with, that we're going to drip this solution into. So we need 1.28 times 10 to the minus 6 moles of sodium carbonate. Well, we can only add the sodium carbonate as a solution, so we need to know the number of liters of that sodium carbonate solution required. So we require 1.28 times 10 to the minus 6 moles of sodium carbonate. We'll multiply that by the fact that we know every liter of this sodium carbonate solution contains 0.00500 moles of sodium carbonate. How do we know that? Because that's the concentration of our sodium carbonate solution, just turned upside down to get moles to cancel out, leaving liters. And then we can, of course, convert liters to milliliters. So it turns out that we need only 0.26 milliliters of our 0.00500 molar solution of sodium carbonate to get enough carbonate in our 1 liter of solution to precipitate lead carbonate and bring the concentration of lead ion remaining in solution down to 12 parts per billion. Now, 0.26 milliliters is a pretty small amount of solution that would need to be added. So a precise pipette would be needed to measure out this small of a volume.